These are the 4.1 Part 4 notes, polynomials and their graphs. And what we're going to be doing today is we're going to be taking all the information which we've already learned and we're just going to put it all together and then graph a polynomial. So everything that we've had for the past 3 days, learning about the degree of the polynomial, learning what that means about the polynomial, what that means it looks like, etc. We're going to apply all of that at once. Now, I'm going to be going through a lot of things as I graph these polynomials. I'm going to be giving you a lot of information. And I don't break it down a lot in the notes, but when you get an exit ticket, when you get a quiz, when you get a test, I'm going to break down everything I want. I'm going to have you find the roots. I'm going to have you establish the multiplicity. I'm going to have you tell me whether or not it touches or crosses the x-axis. I'm going to have you tell me what the graph ends up resembling. I'm going to have you tell me what the end behavior is. Basically, I'm going to be giving you step-by-step instructions on how to graph it with my question. Because as we go through polynomials, as we answer these, we need to be able to graph them, but graphing them is going to come from a lot of the information we found. So to graph a polynomial, we just take all that information, we apply it all at once, just like I said, and we can also test a few points. One thing I do want to say is these graphs are not going to look perfect. We're going to be making a lot of assumptions on what the graph looks like, and we're just going to be using the best guidance we can to make the closest approximations. Here, unless we have graphing technology, we're not going to be able to make a perfect polynomial. We can go through and we can make a pretty darn close polynomial. We can make a lot of good looks, but at the end of the day, these aren't going to look perfect. On quizzes, exit tickets, tests, etc., as long as you've hit all the key information and your graph matches what your key information looks like, well, then we're going to be pretty good. And I'm going to say, all right, this polynomial might not be a perfect polynomial. Yes, you might have your maximum a little bit off. Yes, your minimum might be a little bit off, so on and so forth. But at the end of the day, you've got a pretty good looking polynomial and it looks pretty much correct. As you go to calculus, a lot of the things you learn in calculus make you graph this better. You'll learn how to graph polynomials with much more accuracy. But right now, we kind of have these, I'm going to call them like 85% graphs. Like we know the roots, we know the x-intercepts, we know the end behavior, we're going to know multiplicity, we know what it's going to look like at each x-intercept and root, and we're going to be able to test a few points to get a few more points that look pretty good. So we're going to have like 85% of the graph. Once you get to calculus, you learn how to graph 100% of it just based off the equation. So let's break it down. Let's start looking at this. So graph the polynomial, f of x is equal to x squared times x minus 2. First thing I'm going to do is expand this. This is going to matter at the end, so I've got x cubed minus 2x squared. This will matter at the end. I do need to know that this is my standard form. And I will make sure I establish that this is just standard form. Next thing that I want to look at is my roots. Almost always a good thing to look at with polynomials is your roots. I've got x squared, which means you have a root at 0 with a multiplicity of 2. This is an even multiplicity. Since it is an even multiplicity, that means it touches the x-axis. We have a root x minus 2. This root is going to be positive 2. This multiplicity is going to be 1. This is going to be an odd multiplicity, therefore it crosses the x-axis. The graph with f of x cubed, its first term is x cubed. So for large values of the absolute value of x, the graph will resemble x cubed. This is odd. This is third degree. Let me change colors. Third degree, which is an odd degree. This first term of 1x cubed, we have like an imaginary, like assumed positive 1 there. So since this is a positive 1, it means it has a positive coefficient. of the leading term so this means that it is positive odd, which means that it looks like this, which in mathematical terms, that's what it looks like. I would expect you to say as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So I've got all this information. This is a ton of information that I have gathered from this graph. And I'm still going to get a little bit more. So first, I know that I'm going to have a point at 0 and a point at 2. So I'm going to have an x-intercept here, and I'm going to have an x-intercept here. I know that it's going to touch this x-intercept, and I know that it's going to cross this x-intercept. So far, this makes sense because I know that prior to getting this x-intercept, it has to be going in this direction forever and ever. Just like after this x-intercept, it has to be going in that direction forever and ever. So that matches up with my positive odd rules that as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. But this is not enough to kind of know what my graph looks like. I do want to test a few points. Now, how do I test points? I'm going to test a point before my first x-intercept, between my two x-intercepts, and then after my last x-intercept. So I'm going to test a point here, I'm going to test a point here, and I'm going to test a point here. What points I'm going to test? I'm going to test the easiest ones, the ones that make the most sense. I'm going to test -1, 1, and 3. These are the points closest to my first x-intercept, the easiest point in between my x-intercepts, and then the last point after my x-intercept. And this is just going to get me like a few ordered pairs to make my graph a little bit more accurate. So I'm going to find f of -1, I'm going to find f of +1, and I'm going to find f of 3. I've got -1 cubed minus 2 times -1 squared. So I've got -1 minus 2 times +1. I've got -1 minus 2. I've got -3. For f of 1, and let's change colors on this, I'll do f of 1 in red. I've got 1 cubed minus 2 times 1 squared. That's 1 minus 2 times 1. This is going to end up being -1. And then f of 3, let's do this one in, let's do this like brown. So f of 3, I'm going to plug in 3 cubed minus 2 times 3 squared. I end up with 27 minus 2 times 9, 27 minus 18. This is 9. So I'm going to end up with the points, and I'm going to put this in on my graph. -1, -3. -1, +1, -1, and then 3, 9. Now I'm going to graph my polynomial. As x approaches negative infinity, y approaches negative infinity, so that means it's increasing. I've got an arrow going in this direction. It touches my x-axis at 0 and then comes back down. I know that it's going to get to this point, 1, -1, and then it will come back up and then cross the x-axis. As it crosses the x-axis, it's going to go through this point, 3, 9, and then go up. Now I can look at all the information I have, and I can do a couple quick checks based off of what I know, based off of how multiplicities work. Does this graph make sense? So first of all, the fact that this is a positive odd graph, and with positive odd graphs, this is kind of what the end behavior should look like. As you move to the left, you should have an arrow pointing down. As you move to the right, you should have an arrow pointing up. Put mathematically, as x approaches negative infinity, y approaches negative infinity, that means left down. As x approaches positive infinity, y approaches positive infinity, that means right and up. That's what my graph looks like, so that's good. I have a root at 0 that touches, which I currently have, and that makes sense because my two test points around 0 were both negative. So as I came up to 0, I touched 0, and then I should be going back down. That's what a root touching the x-axis means. I came back down to that point at 1, -1. It goes through that point, and then it goes to, and then it should come back up to my root at 2. At 2, it should cross my x-axis, and I have more evidence to prove that it does cross the x-axis because when I plug in 3, I get a positive number. It changes signs. So now I've got a full polynomial here. I've done a quick check based off what I know. I've looked at the end behavior. I looked at the fact that this is a positive odd polynomial. Its leading term is x cubed, so it has a positive coefficient of positive 1. It's an odd degree because it's a third degree polynomial. I looked at that end behavior and it matches. I looked at my two roots and I looked at their multiplicities, where they should touch and where they should cross. Based on the test points I found, based on the fact that the test points around 0 are the same sign, based on the test point after 2 is a different sign, it matches up with where my roots should touch the x-axis versus where my roots should cross the x-axis. So there's a lot of information here, and I know that I threw a lot of information at you all at once. When you do this on a quiz or test, it will be like A, tell me what the degree of the polynomial is. B, tell me what the leading coefficient is. C, tell me what the roots are and if they cross or touch. D, so on and so forth. I'm going to be leading you to how to graph this. If I just threw this polynomial at you and said graph this, that would be so overwhelming. I realize there's a lot of information here. Don't worry, on a quiz or test, I will break this down more. All right, graphing example number 2. This one's a little bit more difficult. First, let's start with expanding it. I know that eventually I'm going to need the leading term, so I'm always going to expand my polynomials. Right now I've got negative x times x squared minus 4x plus 4 times x plus 1. I've got negative x cubed plus 4x squared minus 4x times x plus 1. I will now distribute every term. I've got negative x to the 4th plus 4x cubed minus 4x squared minus x cubed plus 4x squared minus 4x. Combine my like terms, negative x to the 4th plus 3x cubed. These x squareds actually cross out, minus 4x. So this is what my polynomial will look like when expanded. So now I'm going to jump a little bit. I will think about end behavior before I think about roots. That's another way we can do this. It might be easiest to think about it after you expand your polynomial. So here I know that this is a 4th degree, which is even. Your leading coefficient, your first number, is a negative 1. So this means that this is a negative even polynomial. And since it is a negative even polynomial, that means it's going to point down in both directions. Or as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. That's the mathematical way to state this. I have that little drawing, but basically as x approaches negative infinity, y approaches negative infinity. As my graph is going towards the left, my y values are going down. My arrow's pointing down. As x approaches positive infinity, y approaches negative infinity. As I move towards the right, my arrow's still pointed down. My y values are still becoming more negative. All right, so we've got a whole bunch of information here. Let me reduce this so I get myself some more space. All right, cool. Now I'm going to think about my zeros. I've got negative x, which means that I've got a root at 0 with a multiplicity of 1, which is odd, which means it will cross the x-axis. I've got a root at, or I've got a factor at x minus 2, which means I've got a root at 2 with a multiplicity of 2, which is even, which means it will touch the x-axis. And then I have x plus 1, so a root at negative 1 with a multiplicity of 1. This is odd. It will cross the x-axis. So now I'm going to go ahead and just plot those 3 points. I've got -1, I've got 0, and I've got 2. So I've got those 3 points. When I test points here, I'm actually not going to test the point between -1 and 0. That's going to be a fraction. I'm not going to work with a fraction. I'm actually going to see if I can kind of work out with the other things to make the graph still work. I still want to have 3 test points kind of at a minimum, but I really don't want to work with this fraction. That's going to make my life a little bit harder, and based on what I know about how a polynomial should look, I should still have enough to check myself here and see if this makes sense. So the 3 points I'm going to test are going to be f of -2. I'm going to test f of +1, and I'm going to test f of 3. I'm not going to test that point again 1/2 because I'm just going to see what information I can gather from these. So when I plug in -2, I'm going to plug it into this original equation too. That's one thing I want to note. When I went up here, I plugged it into the expanded polynomial, and that was okay. I can plug it into the expanded. I could have also plugged it into the factored form. Here I'm going to plug it into the factored form. Now you might be asking, Mr. Yehlen, why are you plugging this one into the factored form versus that one? Well, this one's a 4th degree polynomial. I don't want to think about things, I don't want to think about something multiplied by itself 4 times, especially 3. That starts giving me really, really large numbers. Thinking in factored form gives me numbers which are much more manageable. My highest term here is a squared, so when I plug it into the factored form, I only have to think about squaring a number, not raising something to the 4th power. That's a little bit more manageable. So when I do f of -2, I've got -2 times -2 minus 2 squared times -2 plus 1. This gives me 2 times -4 squared times -1. This is 2 times 16 times -1. This is -32. So I've got a point, -2, -32. I will now do the point f of 1. I have 1, -1, times 1 minus 2 squared times 1 plus 1. This is -1 times -1 squared times 2. This is -1 times 1 times 2. This is -2. And then finally, I have f of 3. As I plug this in, I've got -3 times -3 minus 2 squared times -3 plus, or times +3 plus 1. This is +3. Times +3 plus 1. I end up with -3 times 1 squared times 4. This ends up being -3 times 1 times 4. This is -12. So now I've got the points to -32, and to count this, I'm actually going to have to change the scale of my y's. So I'm going to change the scale of my y-axis here to be by, let's say, we're going to change this to be by 4s. This is going to work out well for me, because now the point -2, 32 will actually fall down here, because when I do 8 times 4, that's 32. So this is the point -2, 32. I'm going to have the point 1, -2, which is going to fall halfway in between here. And I'm going to have the point 3, -12, which would fall right here. This is negative even, so that means as I move left, it should start down. It's going to cross the x-axis at -1. I found that at my root of -1, it's odd, so it crosses the x-axis. And it crosses the x-axis at 0 as well. So it's got to come back down at some point, cross the x-axis. It's going to move through this point and then come back up to its next root at +2. And we found that it touches the x-axis at +2, and then it's going to come back down, and it's going to come back down through this point. So really ugly graph. Not the prettiest here. Let me see if all this matches up. So here, I've got a negative even graph. That makes sense to me. Both my arrows are pointed down, which is what negative even means. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. As I move to the left, my graph is going down. As I move to the right, my graph is going down. I've got I've got roots at 0 and -1, both of which cross the graph, and based on my graph here, they are both crossing. I've got a root at +2, which is touching the graph, and that makes sense. All my test points add up, and they make sense given what these rules are. If I tested 1/2, I guarantee you I would end up with a positive value. Again, I'm not going to test 1/2, but it would be a positive value. Now, I do want to state, Mr. Yehlen, where did you make your maximum? How did you make this little area here? I just guessed. I don't have the 0.1/2. I have more than enough to graph this. I have no clue what this part of the graph looks like. This part of the graph could totally look bizarre. That part of the graph could look something like this. That graph could totally look something really, really bizarre like that. I didn't test the 0.1/2. I have no clue what that y value is. It could be an extremely large y value. It could be an extremely small y value. I just made an estimate. And that's okay, because I still have made a polynomial which fits the specifications. Yes, I could test 1/2. Yes, I could get a much more accurate graph, but here testing 1/2 sounds a little hard to me. I know this shocks you. I can do fractions really well. I'm not scared of fractions, but I still avoid them. If I don't have to do a fraction to do something, I'm not going to do it. I can make a much more accurate graph with a fraction. Yes, you are correct. Do I need to here? Absolutely not. I have enough information here to back up that everything that I've done is pretty much correct. Yes, I could get that point, but I don't need to get that point. And because I don't need to get that point, I'm not going to. If you had something like this on a test or a quiz, if you didn't test that point, but your polynomial still matched up all the information you had, this is a correct answer. You don't need to know what that value is. It does not need to be perfect. It could be a little bit off. All right, last thing that we would have, which of the following graphs could be this graph? I'm going to ask you something like this on your practice quiz. You're going to see something like this on your quiz. You might see something like this on one of your finals. This is a really good question. You're just given a bunch of information, and then it's basically looking at the information. What can you gather from it? So we're going to start off with the fact that your leading coefficient is +1, and your degree is a 4th degree. So this is positive even, which means that as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity. They both have to be pointed up. I can immediately eliminate d based on this fact because d just does not fit the requirements that I have here. Next thing that I'm going to look at here is my y-intercept. My y-intercept is going to be -6. You'll quickly see as you plug 0 into all those terms, those go away. And I can just immediately say here that f of 0 is -6. That means I have to have a negative y-intercept. That could be b or c. I have no clue what this scale is. That's fine. I can say that it's not this graph here. And then lastly, I'm going to look at my max number of turning points. I've got a 4th degree, as I've already said. That means at most you have 3 turning points. And since I have at most 3 turning points, that eliminates C because I've got 1, 2, 3, 4, 5 turning points in C. Here I've got 1, 2, 3 turning points, a negative y-intercept, and it's matching up with that positive even. So B is the only graph here which could match up with that function. You guys have a homework assignment tonight. This is just graphing things. So you'll see that I have F only in all caps. That's because you've already done all the other information. You've already done A through E. A through E is based on finding your roots, finding your multiplicity, everything. So you've already done all this. Since you have all this, you don't need to do A through E again. All you need to do is take last night's homework, which I said to save because it's going to help you with tonight's homework, and then apply all that information and then actually graph it. So if you have any questions or concerns, please reach out to me as soon as you can, and have a great night.